Good morning, everybody, to our next calculus class, where we are moving on. We have all the derivative properties that we are going to need. Hopefully you have practiced, and now it is time to add a basic function to our list. Now, because we're introducing a basic function that you might have seen in some form before, I assume that you've never seen it, so I'm going to start from scratch. And we're also immediately after that asking the derivative question, what is the derivative of this new function? The discussion is going to take us about 3 or 4 sessions. We are going to start our discussion on exponential functions. And for that topic, I'm actually going to start at the end and then loop back to it, and we'll see how this goes eventually. So we're going to have a function, let's say of a certain form or type, and it's going to be a number to the power of x. And that's unlike any function we can get by way of a polynomial or combining polynomials in any obvious way. The variable x is now in the exponent. And a is called the base, and we are going to have a b positive. Because if I have a negative number, then for certain values of x, it's not going to exist, and then I have some continuity problems. We're going to avoid all of that. So if I take, for example, y equals 2 to the x, I like 2 as my starting example, base 2. Because it's easy to work with, I can make a little table of x and y values. Let's say I have -2, -1, 0, 1, and 2, and maybe a 3, and so on. Then for x equal to 0, anything to the power of 0 is 1. For x equal to 1, it's 2 to the power of 1, which is 2. Then 2 squared, which is 4. Then 2 cubed, which is 8. So it's easy enough to make this table. 2 to the -1 will be 1/2. 2 to the -2 will be 1/4, and so on. So regardless of the x value that I look at as input, my y values are always positive. The further left I go, the smaller this fraction becomes, because the negative exponent moves it to the denominator, and then I have 1 over something that grows. And the further right I go, the bigger the y value becomes, because I'm looking at larger powers of x. So if I visualize this with my graph, I have a function, a graph that sits above the x-axis, slowly getting smaller to the left, blowing up to the right, something like this. Now it's actually a little steeper in terms of how fast it picks up, but I like to have a nice smooth shape that I can remember. So some properties: if x approaches positive infinity, then y also approach positive infinity. If the x values get bigger, the y values get bigger. It doesn't matter how fast, it's just the direction that it's going. So I could, if I wanted to, summarize this by saying the limit x goes to infinity of 2 to the x is infinity. Also, if x approaches, no, not 0, negative infinity, I'm going far to the left, then it's not too difficult to be confident that y is going to go to 0. I can write that in my limit notation. 2 to the x is going to be 0. So that means I have a horizontal asymptote. And contrary to what I saw with rational functions, the horizontal asymptote is the line sitting on the x-axis. So that is the line y equals 0, matches that 0. It's only a horizontal asymptote on the left side only. That doesn't make it any more or less of a horizontal asymptote. But what I saw with rational functions is any horizontal asymptote, if there is one, is a horizontal asymptote on both sides. The graph will approach it when I go far to the left and far to the right. For this kind of function, I don't have that symmetry anymore. What happens on the left is very different from what happens on the right. But I do have a horizontal asymptote, and it happens to be on the left. All right, so that's my basic exponential function with an example. And if I change the base from a 2 to a 3, it's just going to be a little bit steeper and going to 0 a little bit faster, but the general shape and the trend and the properties are going to be the same. So I pick an easy number like 2 to just easily get some numbers for the y values. So we have a basic function that I now can add to my library, and technically I have a ton of them, just with different base values. It could be a 2, 3, 4.7, whatever, as long as it's positive. So I can practice my transformations. Whoopsie, what happened there? A little laggy. Practice my transformations on this basic function. Let's say we have y equals negative 2 to the x minus 1 plus 3. Just picking nice numbers to make the graphing easy. So then I'm going to start with 2 to the x. I'm going to take it to, I prefer the handling the numbers in front, so there's a negative 2 to the x. And then we'll take it to negative 2 to the x minus 1. And finally, I guess we'll go over here to our end result like that. So let me just set up my graphs. I will do the other one last, a little bit later. Okay, so I have my basic exponential shape, indicate the y-intercept at the very least. Then, when I multiply the right-hand side by a negative 1, it flips it vertically. So now I'm going to have a shape like that, just flipped around, and my y-intercept will be negative 1. Then, when I replace x with x minus 1, that shifts everything to the right by 1 unit. Let me extend this a little bit here. Y and x. So then I'm going to shift to the right. Whew, it's a wobbly line. The slower I go, the worse it gets. So now it doesn't look like I did much. My previous y-intercept is now sitting up here, -1 and 1. I just make the scale whatever so that I can have a nice shape. Then, lastly, I have to shift everything up by 3 units. Maybe like that. Hopefully we have enough space here to just get the idea. So my horizontal asymptote, which was at y equals 0, is now sitting a little bit higher at y equals 3. My point that I kept track of that was my original y-intercept is now going to sit at 2. So it's actually a little flatter like that, right? And I'm just going to say that is a 2. No, not that. No. Let's make it even flatter. It actually jumps up very quickly. So let's say that over there. Oopsie, over here is a 1 and a 2. Because it was at y equal -1, shifts up to y equals 2. Let me get rid of this over here. That shouldn't be there. And I can now calculate the new y-intercept if I wanted to. Let's do it over here. My graph didn't, just one. My graph didn't move around in a way that I could easily keep track of the y-intercept. I can't trust my graph. So I simply set x equal to 0. And so I get -1/2 plus 3. So I get -2.5. But I can't trust my graph that, oh, that looks like halfway. So yeah, it's obviously half. No, I don't have the nice shape that I might think I do. It accelerates very quickly once it blows up. So it's best to just calculate it and be sure. All right, so I have a new kind of basic function that I add to my library, the exponential function. Different bases, the shape is the same, with one observation. Sometimes in your pre-calculus class, they might make it sound as if the function 2 to the x and the function 1/2 to the x are fundamentally different, and I need to memorize them separately. So here, remember, this is now my basic one that I have, y-intercept of 1 and so on. I don't really feel the need to remember a different, or to see the second one as a different function, because I can simply rewrite this as 2 to the -1, everything to the power of x, and therefore 2, oops, my 2 is so low, therefore 2 to the -x, which means this is just a transformation replacing x with -x, which means what happens to the basic graph? It flips vertically. Whoopsie, maybe not that flat. Drawing this way is so hard for me. Woohoo! Let me see if I can make it maybe incremental and have it be a little better looking like that. So it is just a reflection of my exponential function when the base is greater than 1. When I have a little positive fraction, it's not a different graph, it's not a different function, but I have seen in the past that they make it sound as if you have to memorize 2 versions of this. No, one is just a transformation of the other one. And of course, something I forgot to mention, technicality, but a is never going to be 1. Otherwise, the answer is always 1, and I don't really have a graph of the same shape. But as long as it's positive, fraction or not, or bigger, doesn't matter. It's still the same basic shape that I remember, only 1. And if I have to transform it to get to slightly other versions, it's still the same original that I start with. But if you remember it in a different way, that's totally fine as well. Okay, so that was one observation that I want to make. And I'm not going to spend too much time practicing transformations and all kinds of things because chances are you have seen this before, you do remember it, and on top of that, it's not the most complicated graph either. It's actually a quite nice, simple one. It just doesn't have the symmetry that I'm used to in polynomials. So it's definitely not a hard one to get on top of. Next, I just want to refresh our memory. You have done these things before. We're not making a big deal of exponential equations, but they are going to come up now and then. So I do just want to remember, how do I handle this? How do I solve for x if x is in the exponent? Well, there is a basic kind of equation, like maybe something like that, where if I rewrite the base as 3 squared, and I notice that 27 is 3 cubed, I can see that this is 3 to the power of 2x equals 3 to the power of 3. Now there's a property of exponential functions and or equations that if I have the base to the power of something and the same base to the power of something else, I did not allow myself a lot of space here, then that is always going to be equivalent to the exponents being equal as well. There is no way. Now that comes from a property of certain kinds of functions being one-to-one or injective and things like that, that we don't necessarily have to dig deeper. We just have to notice that if I can make the bases the same, the only way that this equation can be true is if the exponents are actually the same, leading me to the value of x. But regardless, I need to exploit a property, I need to do something to get x on the base level. Right here, in the previous step, it's in the exponent level. I can't solve it there. I want to write x equal to something, and that is on the base level. And I use this property in the box to get x out of that exponent level. In this basic type of equation, it's as simple as that. But yes, there are more complicated exponential equations, which we will come back to when we have the tools to handle them. So this is the first kind of basic exponential equation that I want to just remember, because I'm sure you have seen this before. Let's just do one more. 32 to the power of 2x minus 1 equals 128 to the power of x plus 3. Now at this stage, given the tools and knowledge that I have to have the same base. And the base is going to be 2. 32 is 2 to the 5. If you don't remember it, you can just do some trial and error. 128 is 2 to the 7. So I can then simplify this with my exponent property. It's going to be multiplication, 5 times 2x minus 1. 2 to the 7 times x plus 3. Because the bases are the same, it has to be that the exponents are the same. There is no other way. So then I have 10x plus 5 equals 7x plus 21. I've now gotten the x that was in the exponent level out into the base level, and I have 3x equals 16, x equals 16 over 3, and I'm done. All right, so these kinds of exponential equations, meaning equations with the variable in the exponent level, you would have seen before. I'm just doing a couple of examples to refresh our memory. We're not going to do too many of these, but the issue of having the variable in the exponent level is going to come up in simple ways now and then. All right, so now we have our basic function here. There it is. Have the value of a be whatever you want within reason. The basic shape of the exponential function, given some transformations, is going to be the same. So we have this new kind of function. It's nice and smooth. So it's reasonable to start asking about slopes of tangent lines and rates of change if something grows like this. How fast does it change? All those are linked to the derivative. Question in the chat. Let's go back here. Why did the sign change on 2x minus 1? Because I am not thinking clearly. Or let's pretend I did it on purpose to just see who is paying attention. And congratulations, it turns out you are paying attention. You passed the test. And you are still awake or already awake. So give yourself a pat on the back. You passed. There you go. No reason whatsoever, of course, it can't magically change from a minus to a plus. Let's pretend I did that on purpose to see who's paying attention. I would never make a mistake. No way. Okay. That issue aside, I have my function. The whole question in calculus, or at least in the beginning, is the derivative question. So our goal, and it's not going to be a simple goal overall, is to find the derivative and to understand of the function a to the x. So I call this my general exponential function because the base can be whatever, general base, 2, 3, whatever. Okay. So that is the question. Well, this is a new function. And whenever I have something new, I have to go back to the limit definition. Whether I see that happening or not, that is where we go. Back to limit definition. Now, the way I like to do this is to see, how does the story go? What does it look like? I will make it very clear, you do not have to ever do this limit definition on the exponential function. Okay, let's make that extremely clear. But I find that you lose a little something. Something's missing if I just slap it on the screen and tell you what the answer is. To at least see a little bit of the story and see what the limit definition looks like, and then go, "Ugh, I don't want to do that." You've gained some knowledge, and you have a little bit more of an appreciation. So that is what I'm going to do. But again, you do not need to do it. Just sit back and enjoy, or enjoy the fact that you don't have to do it as we go on, and you'll see what I mean. So That is our setup. Let's take an easy example, because 2 to the x, I have a good feeling about 2 to the x. It's my best chance to understand an exponential function using a 2. Okay, so I want to find what is the derivative of this function. Well, limit definition. What else can I do? It is the limit. I can at least set it up. You have to know how to set it up, right? H approaches 0. F of x plus h minus f of x over h. Now, we might have used a c for a specific x value, but of course, I don't want to do it for a specific number. I want to do it in general. I want to see what the limit definition tells me, so at least once, so I can get away from it, which was my goal for all the other properties, right? I don't want to spend a lot of time with the limit definition, but in order to prove the product rule, in order to prove the power rule, in order to prove all those properties, I had to go through the limit definition, even the chain rule, but I didn't even want to show that because that is quite complicated. It all goes through the limit definition in one way or another. So this has to as well. So let's do it. Let's see what that looks like. Okay, well, first I have to use the function. So in this case, it's 2 to the x, or 2 to the whatever the input is. Now the input is x plus h, so it's 2 to the x plus h. And this one's input is x, so 2 to the x, of course, over h. So I need to simplify this because I can't plug in 0 for h. I'll be dividing by 0, and that is not going to help me in any way. So there's some exponential properties. 2 to the something plus something else is multiplication. 2 to the x times 2 to the h. Oops, that is the very ugly h. H. And then I have minus 2 to the x over h. So now I see there's 2 to the x in both terms, so I can take it out as a common factor, 2 to the x. And I have left 2 to the h minus 1 over h. Now there are some limit properties here that I didn't explicitly discuss because we, in my opinion, never need them. So why make a thing of something that I don't need? And I have mentioned this before, that if in the limit I have something that doesn't depend on the limit variable, which is h in this case, it's sort of like the constant times a function property. I can leave it in front and it doesn't actually change the behavior of the limit because it doesn't have any h's in it. My h's look terrible today. So there are some limit properties happening behind the scene allowing me to do this. Now remember, this was our derivative, right? For whatever x value we have. The function's defined everywhere, so you can plug in any x value you want. Regardless, if h is the changing variable, x doesn't change. 2 to the x is constant with regards to that. Okay, so I have this thing that I don't know what to do with. Does it exist? It's a limit, so I'm asking, does it exist? Is it a number? What is happening to it? Now, what one can do is you can take smaller and smaller values of h, plug them in, and calculate this 2 to the h minus 1 over h, and it seems like it does exist. It seems to be approaching a number, seems to be pretty stable. And that number is something like 0.69315, and there's a whole bunch of decimals. So there's a number. It's a number. So what I have is my derivative. It's not that nice. I have 2 to the x times some number. Now, I don't really look at this number too closely because I realized that if I had a different exponential function, 2 was just my example base. I could have any base. Then I would have that base in the limit, and that would change the number. So for every different exponential function, the some number part that gets multiplied is going to change. So this is going to be some number that depends on the base, and that's certainly not ideal. First of all, it's a non-repeating, non-terminating decimal number. The decimals never stop. And it's going to be a different number for every base that I look at. So we've made some progress, but it's certainly not as great as I would like it to be. Okay, that's the story. So they sort of got stuck when they got to this point. But around 1683, which was before the calculus started, a very famous person by the name of Benoulli, they were actually brothers, he was looking at interest rate calculations and nothing to do with calculus. He didn't care. And what he had to investigate was a limit that looked like this. It was 1 plus h to the power of 1 over h as h goes to 0. And this features in one form or another in compound interest formulas. When you let the compounding period shrink down to 0 or close to 0, you get this kind of thing that you have to evaluate. And he did it by trial and error and maybe derived some properties and realized that it existed. It's a number. This approached, sadly, also a non-repeating, non-terminating decimal number, 2.718, whoopsie, next one is a 2, 28182845904523536, and I don't remember the rest. Ooh, that is an ugly 3. As soon as I write something and the lag kicks in, it makes my pen wobbly. So decimals never stop. But there is a number that this approached. And that's what he needed, and he moved on with his life. Then when they were looking at the calculus question of finding derivatives of this exponential function, we're now back to this sticky point of having 2 to the x times some number. And we don't know what to do. We sort of got stuck. They decided, well, let's take this weird number and let's call it E, after the person that made the next step, Leonhard Euler. Let me just make a new page. He said, let's take this number as the base and see what happens. As weird as that number is, he took this E, which is the limit, h approaches 0, 1 plus h to the power of 1 over h. It exists, 2.71828 and so on. Let's take that as the base. As unnatural as that seems, let's see what we get. So now our function is this weird number to the power of x. Now remember, I can have any base. As long as it's not 1 and it's positive, I have an exponential function. I have infinitely many exponential functions. By changing the base, this is one of them. Now following the same situation, I would get to this point in the this arrow here at the top here. I would follow the same limit definition, and I would get e to the x times limit h goes to 0. What did I get here? The base, original base to the h, minus 1 over h. It would follow the exact same. Changing the base replaces the 2's with whatever the new base is, and I have the same issue. However, if I now plug in what E is, in terms of its Bernoulli definition, it's 1 plus h to the 1 over h, all of that to the power of h, minus 1 all over h. So I have something to the power of 1 over h and then to the power of h, and those cancel each other. So what I am left with is 1 plus h minus 1 over h. The 1 and the negative 1 cancels, the h's cancel, and this whole thing is equal to 1. And so this extra number, this sum number that gets multiplied in the derivative, depends on the base, but when I take this weird number e, which is a non-repeating, non-terminating decimal number, as the base of my function, then this extra number is equal to 1. And that's only going to happen if I take that as the base. Which means then the derivative is just e to the x. My function is e to the x. And this is the only function that has as derivative the exact same function. Remember, it's an exponential function. It's positive, so I can graph it. There it is. But if I take this as the base, remember this is the original function. These are the y values. This is the derivative. That's the rate of change. So that means wherever I am, if I'm over here, I get a y value. That y value is the same as the slope of the tangent line. So the graph is increasing at a rate that is the y value. So then I go up, right? It's a positive value, so I increase. Then I get a higher y value, which means the slope, which is the same, is even steeper. So it increases faster, and it increases faster. The rate of change is exactly the same as the function value at that point. And it's in a way, if I forget what the number e is, it's in a way the simplest situation it could possibly be, in that the derivative is the function itself. It is the exact same. No adjustment at all. I'll write it over here. Derivative of e to the x equals e to the x. Literally nothing changes. It is the simplest and most natural thing I could do, is to not do anything. So we call this the natural exponential function. And e is the natural base, which is quite ironic because it is hardly a natural number. It's actually not a natural number at all. It is a number that has infinitely many decimals that never repeat. Yet this number makes calculus so much simpler than it could have been, in that the rate of change of this exponential function is exactly the same as the function itself. Now, we have to pause the question of what the number is, what this sum number issue is. If my base is anything else, I have a number popping out. If it's anything other than E, for example, if the base is 2, I have this 0.69315 number popping out. Where on earth does that come from? If I have a different base, I have a different number popping out. And it's not as clean as the natural exponential function. If my function is 2 to the x, the derivative is 2 to the x, but scaled with some number. And I don't know what that number is right now. We're going to have to wait until the very end and loop back and better understand what the relationship of this number is to the function itself. For now, we found the simplest case with the base E. So all I want to do in the remainder of the time is to just get used to this in case you've never seen it before. Some pre-calculus instructors show you the E with some hand-wavy explanation of where it comes from, just so you have seen it before, that when the calculus topic comes in, it's not the very first time, but it's certainly not a requirement that you've seen it before. So now I just want to do some examples with this natural exponential function. So let's say I have a function and it's e to the 4x. I know that if it's just e to the x, well, the derivative is exactly the same. I change nothing. It is the best case scenario. But if I change this even a little bit, then let's change it like this first. Let's do this first. Let's put the 4 over here, like that. So now I want to find the derivative. My question to you is, what is the first property that we're going to use to find this derivative? I see we've lost some people. As soon as I say, oh, you don't have to be able to duplicate that limit definition, people just say, oh, disconnect, I'm out. I'm going to do something else. You lose a little something if you don't hear that story, I feel. You get an appreciation for how weird it is. This E, it's not a simple number, yet it is the simplest function. That's weird. It's weird. What is the property that I'm going to use first to find this derivative? That is my question to you. Nothing's changed. I still have properties. It is not the power rule because I don't have x to the power of n anywhere. This is a completely different function. It has its own property, which is this guy. This is a new property, if you will. Property telling me how to handle an exponential function. But my question was, what is the first one? What is the first property? First property is constant times a function. Because I need to now isolate this e to the x. So for the love of all things good and pure, do not make it red. I'm going to make it red. No, like a violent, scary red. That's pink. This one. Do not say this is x times e to the x minus 1. Then I'm sorry, but this is not what's happening. You have missed the point completely. This is a completely different function. It doesn't even look like a polynomial in any way. This is not what is happening. But sometimes you have to think that it is, and then when I correct it, that sticks in your memory. And now you're going to remember. Those that left the class and just do their own thing, I guarantee you some of them are going to do this very thing because they didn't stay, they didn't contribute, they didn't learn. I see it every semester. People do this. And it's because they don't come to class and they don't try and they don't say anything. That's how we learn and remember. Don't feel bad about anything that you say. That's how you're going to remember. So this is now a new property that I just memorized, but it's so easy to memorize. You literally copy it. There is no adjustment of the function. I'll just write it over here. Oops. It is the simplest thing ever. You just copy it down. For the natural exponential function, the derivative is the function itself. Literally nothing changes. It cannot be easier. Cannot be easier. Okay. But we had to do this now to realize, oh, wait, no, not power rule. But now I'll remember. Okay. Let's make it something else. Maybe e to the 4 times x. What is the first property that I'm going to use now? Here is where it gets a little, maybe less recognizable because there are no brackets. This is a function of a function. Let's say u is 4x. Then my function is e to the u. Now, my exponential property, if you want to call it that, only says if my variable is x and I have e to that variable, then the derivative is e to that variable. These circles have to all be the same. You can call the variable u, but that variable has to be the only thing in the exponent. And it's not. There's a 4x when my variable is x, meaning that there is a function of a function. It's the exponential function applied to the 4x function, which means I need the chain rule. So now the derivative with respect to x is the derivative of the function with respect to u, derivative of u with respect to x. First part of the chain rule says take the derivative of the outside function, and now it's set up for this property in the box because the variable is the only thing in the exponent. And because it's e to that variable, the derivative is e to the variable. Second part of the chain rule, derivative of 4x, 4. And then finish it by replacing u with what it is in terms of x. And you're done. So in the case of the exponential functions, it's a little more difficult to recognize where the chain rule is, where the function of a function is, because we don't have the brackets essentially giving it away. Okay. Now, we are unfortunately out of time. You can, I'll show you here. Sorry, my view is wrong. The main one we are needing to practice is problem 7.5, where I just have the base e, I mix it up. We'll have some practice for this at the start of tomorrow, just to make sure. So this is the first step in a longer discussion, clarifying all the issues surrounding exponential function. Ultimately, we do want to know, well, what do I do with this function? What do I do if the base isn't e? But that can only be answered efficiently at the very end.